Okay. Good morning, everyone. Thank you all for turning up, and welcome to the fifth lecture in our series of lectures. So thus far, we've done a fair bit of introduction to radio astronomy and different processes involved with producing radio emission. How do we measure radio waves from astronomical sources, that kind of thing. For today, we're going to change pace a little bit to something a bit more general than that, which is introducing you to the different timekeeping and positional systems that we use in astronomy. So the idea behind this lecture was, from my experience in my PhD, I had a lot of trouble coming to get to grips with all of these different systems that people use, especially if, like me, you don't have a background in something like sky watching or astrophotography or something where people use these kinds of coordinates and time systems. But when you just get into doing observational astronomy, it can be very confusing. People just give you these coordinates or these time codes, and you're kind of just expected to pick up exactly what they mean. So I'm hoping to um, demystify some of that a little bit so that you can recognize some of these systems that we use in astronomy and be able to recognize when they are used, how they are useful, and in what occasions they are not, and be able to convert between them when you need to. Right. So the first thing I want to talk about is how we measure time. So on Earth, our measurement and recording of time is very much based on the motion of the Earth with respect to the sun. So because the Earth orbits around the sun, and it's a periodic motion, our notion of time and the way that we record it is very much cyclical. So we divide our time into years, which is the amount of time that it takes for the Earth to complete a rotation around the sun. And then we further divide that into seasons, which reflect the way that the Earth's axis of rotation tilts with respect to the sun, so that different parts of the Earth get different amounts of sun as we travel around that orbit. And then we further divide it into months, which reflect how long, approximately how long it takes for the moon to travel around the Earth, and then further into days, which is how long it takes for the Earth to complete one rotation about its own axis. So we have these cyclical notions of time, but there are many different possible ways of describing that time. So we can be talking about a local time, what is the time exactly at my position, or we could be talking about some reference time, what is the Greenwich Mean Time, or a sidereal time, which I'll talk about later, or ephemeris time, mean solar time. There's a whole long list of different timekeeping conventions that people have used throughout the years for different purposes. And we can also devise different ways of measuring a year. So we can talk about a sidereal year, a tropical year, a Besselian year, or an anomalistic year, etc. I'll get to some of these as we go on. But in general, in the uh, uh, modern era, we divide our calendar year up into 365 days, defined again by the amount of time it takes for the Earth to complete a rotation. But in fact, the Earth actually takes about 365.2422 days to orbit around the Sun. That's called a tropical or solar year, meaning that if we didn't use leap days, that the error is about 0.2422, which means that in 1,500 years, the seasons would reverse completely. You would have summer in July in South Africa, which would be very bad for keeping track of crops and that kind of thing. So the Julius Caesar was the first to proclaim the the existence of leap days. So he instituted leap days once every 4 years. So it's an extra day to the calendar, which brings up the calendar to 365.25 days per year. So now the area is about 0.08 days a year. And that's fairly small every year, but over 100 years, you lose about a day. So this calendar, called the Julian calendar, was used until 1582. And at that point, it became a problem that the March equinox was happening well before Easter. So you were losing so many days that the date usually reserved for Easter, which is an important date on the Christian calendar, was happening long after the March equinox actually happened. So equinoxes are the times on the Earth's orbit around the sun when the plane of its rotation is exactly square with the orbit around the sun. So it's exact. So the sun's rays are exactly perpendicular to the Earth, and therefore a day is exactly as long as a night. So that happens exactly 2 times around our orbits around the sun. Once in March, around 21st or 22nd March, and once in September. And those dates differ slightly every year because of some perturbations of the Earth's motion around the sun. But generally, the Easter was devised as a celebration of the March equinox. But now you had the case where the equinox and Easter were not happening at the same time, and that caused a bunch of problems. So Pope Gregory the 13th in 1582 fixed this discrepancy by erasing 9 days out of the calendar. He just declared that 5 to 14 October 1582 wouldn't happen. And so they caught up with the equinox, and then also declared that the centennials, meaning the years ending in 00, 1600, 1700, 1800, are only leap years if they are divisible by 400. So that's why the year 2000 was a leap year, but 1900 was not a leap year. So doing that means that you miss out on an extra 3 days every 400 years, which would have been leap days. So it's 0.0075 days a year less. This is called the Gregorian calendar that we use today, and it has 365.2425 days a year, which compared to the tropical year is an error of only 0.003 days a year, which is manageable. So that's the calendar that we use in everyday life. But for astronomy, we need a standard reference time, so that if you are doing an observation here in South Africa, but you want to communicate with somebody in Canada doing this to observe the same object, you need to have some reference time to coordinate that communication. So in general, we use the UTC, which is Coordinated Universal Time, and that's basically the time at the prime meridian. So it's basically the same as the Greenwich Mean Time. If we want to do calculations with time, the cyclical calendar is often a detriment to that. So instead of using the calendar, we use a continuous decimal count of days. So we have defined something called the Julian day, which is the number of days that have passed since 1 January 4713 BC. Don't ask me why they chose that particular date. It was pretty arbitrary, I think. But we've counted the number of days since that, and that gives us the Julian day. And then each new day starts at 12 UTC, so it starts at noon rather than at midnight. And then you can have a decimal value as the day progresses. So to give you an example, today is 6th of September 2024, about 9:15 South African Standard Time, which is in the UTC +2 time zone. So there have been exactly 2,460,559 days since 1st of January 4713 BC. I don't advise you to count those, just you can look it up on Google, or there are a bunch of tools to calculate that. So that's the value before the decimal, and then the time, it's 9 UTC, which is UTC +2, which is 11 UTC, which means it's 1 hour before the end of the Julian day. So 24 minus 1 divided by 24, the decimal is 0.9583 repeating. And then there's another 15 minutes to add to that. So you take 15 minutes divided by 60 is 0.25 hours. Divide by 24 hours gives you that decimal that you add together all of the orange numbers to give you the current Julian date, which is this long timestamp. In astronomy nowadays, we don't tend to use the Julian date. Instead, we use the modified Julian date, or MJD, and that simplifies the Julian date in two ways. First, we get rid of first we move the reference time backwards from noon to midnight, so that the UTC day starts at the same time as the Julian day, and then we remove the first two digits. So this is the current Julian date. To get the MJD, we just lop off these first two digits, and then in the decimals we take negative 0.5. So this is the current MJD, and you can calculate these MJDs, measure them very, very finely to the more decimals you add after the comma, the more precise you're measuring the time, down to nanoseconds, femtoseconds. So I've done some work on pulsar timing, for instance, where you have to measure the arrival times of pulsars, pulses from pulsars very, very precisely in order to model the arrival times. And there we use these MJDs as time codes to record when exactly the pulse arrived, but you have to use as many digits after the comma as possible to do that as precisely as you are able. But the next concept that you need to know is about sidereal time. So in general life, we use solar days, which are measured by the motion of the Earth around the sun. Or another way to think about it is the amount of time that it takes for the sun to go from one point in the sky and do a full revolution around and return to the same point. But astronomers want to define a day relative to the motion of the stars instead. So a sidereal clock, instead of using the motion of the sun, looks at how long it takes for a star to return to the same position. And the sidereal day is not the same as a solar day because the Earth advances around the sun over the course of a day. So this plot on the right, or this diagram, is showing you how this works. So during the day, if you observe a distant star, as the sun advances on its rotation around the Earth, during the day, your perspective of the stars changes slightly. So there's going to be a slight difference um, between a sidereal day and a solar day. So to quantify this, the Earth travels around the Sun in about 365.25 days, but in that time, the Earth rotates about its axis 366.25 times, meaning that a solar day is 24 hours, but a sidereal day is 23 hours, 56 minutes, and 4 seconds. So the sidereal day is equal to the UTC exactly once a year, which is at the September equinox around 22nd September. And then as we go uh, further in the calendar, the UTC and the sidereal time get further and further apart until 6 months later at the March equinox, they are exactly 12 hours apart, and then they start getting closer together again. For an astronomer, the sidereal time is very important to know because this is the time that you need to use to know if your observation target is in the sky. So you should be able to see my screen still. I want to show you, for example, this is the Meerkat observation planning tool, right? If you have a Meerkat observation that you have proposed for, you use this tool in order to plan your observation. At the top immediately, you can see that there are 3 clocks. It shows you in the top right, it's the UTC. So that's the time at 0 latitude, or longitude. And then so it shows the local time, so it knows I'm in South African Standard Time. And then also the big one that it shows is the local sidereal time. So this is the one that you have to use to plan your observations. So then it has this tool that shows you the source elevation, the elevation of different sources as a function of this LST. So if I show you an example of this pulsar, is named J0408 minus 6545. So the right ascension is 0408 and the declination is minus 65.45. I'll get to what that means in a bit. So the declination is negative 65 and Meerkat is located at negative 30 degrees south of the equator. So you can see that the source is up in the sky for most of the day, and it peaks at around 4 a.m. LST. In this case, you can see that at the moment, LST and UTC are very close together. It's only about 30 minutes difference, but that's because we're close to the September equinox. For the most of the year, these 2 times are very different. Here's an example of a pulsar that is the declination is plus 30. So it's uh, uh, 90 degrees away from the Meerkat's latitude, meaning that it's only up in the sky for a very, very short amount of time. And you can use the LST to calculate exactly when it will be in the sky and when its maximum elevation will be. So to get back to the slides. The LST is the thing that you want to know when you're doing an astronomical observation. You can relate the local sidereal time, LST, to the sidereal time at the Greenwich Meridian, which is called GST. So in order to do that, you need to know the longitude of the observer. So for example, Meerkat is at these coordinates, 30 degrees, 42 minutes, 48 seconds south, 21 degrees, 26 minutes, 35 seconds east. So the longitude of Meerkat is at plus 21 degrees, and you can express that in a decimal value. And then if you divide that by 360 degrees divided by 24 hours, which is one rotation, you can convert this to hours. That's 1.4296 hours. And then converting that back to our minutes and seconds, the LST is given by the Greenwich sidereal time plus that time given by the longitude of the telescope. So you can use this equation to calculate the local sidereal time at any observer. You just need to know the longitude. Right. So that's systems for how we measure and communicate time. Now let's talk about systems for describing positions on the sky. So we can think about the sky as a two-dimensional projection. So we can project it into two dimensions, basically a flat dome. And then in that case, we need two values to unambiguously describe the position of an object in the sky. So in general, we use a latitude, meaning how far up in the sky is the object, and a longitude, how far around the dome is the object. And then we can use different coordinate systems which have different origins. So is the origin on the observer, or on the sun, on the earth, or on the galaxy, or some other origin. And it can have a different fundamental planes, basically meaning how do you define your X and Y axes. So this table from Wikipedia neatly summarizes the four different coordinate systems that we use in astronomy. So we use horizontal coordinates, also called altitude azimuth coordinates, equatorial coordinates, ecliptic coordinates, and galactic coordinates. And each one has a different center point, different fundamental planes, and different names for the coordinates that they use. So I'll go through each of these one by one. The first coordinate system is probably the most simple one from an observer's point of view. It's called the horizontal coordinates, and the name tells you basically everything you need to know. It uses the horizon to define the fundamental plane. So we measure coordinates with respect to the horizon. So in this case, the center point of the coordinate system is the observer. So you imagine yourself standing out in a field, and then you point towards the horizon that demarcates the 0-degree latitude. And then if you point towards the star, as you point upwards, the further up you have to point, that's called the elevation or the altitude. It's the distance above the horizon. And that goes from 0 degrees at the horizon up to 90 degrees exactly overhead, which is called the zenith. And then the longitude coordinate is measured from true north. So you point towards true north, which means that's the north pole defined by the rotation axis of the Earth. So it's not magnetic north, it's true north. And then you measure clockwise from 0 degrees all the way around to 360 degrees. So east is at 90 degrees, south at 180, west at 170. And this is very useful to, the azimuth is useful to know if an object is rising or setting. Because objects rise in the east, so that the Earth is rotating from east to west. So objects rise in the east. So if the azimuth is 0 to 180 degrees, you know it's rising. If it's 180 to 360 degrees, it's setting. So this is the coordinate system that we use to point a telescope in a given direction. It's very easy to tell the observer, look at 80 degrees elevation, 30 degrees azimuth, and then you just point 80 degrees up and 30 degrees to the east, and you know exactly where you're pointing. The um, drawback of the system is that objects are always moving with respect to it. So um, the coordinates are defined with respect to the observer, but objects in the sky, their coordinates will always be changing in the system. And that's bad if we want to track sources or to communicate to another observer at a different telescope to say, look at these coordinates, you will see this star. If you give them altitude azimuth coordinates, they won't know what you're talking about. They won't see the same object. So in order to track sources reliably, we want to define a coordinate system that fixes their position to say, if you look at coordinates x, y, you will see this object. And the coordinates that we usually use to do that are called equatorial coordinates. And instead of using the observer's horizon, now we use the Earth's celestial plane as the fundamental plane. So the celestial plane is the plane perpendicular to the rotation axis of the Earth. So it's parallel to the equator. That's why it's called equatorial. And then we define declination, delta, as the amount of degrees above or below that equatorial plane. So 0 degrees latitude or 0 degrees declination is at the celestial equator, and then going up to plus 90 degrees at the celestial north pole. So that's aligned with the spin axis all the way up, and then the celestial pole at negative 90 degrees. And then the longitude we measure with respect to the March equinox. So as I explained, the equinox is the point in the rotation of the Earth around the Sun, where the plane of the rotation is exactly parallel to the plane of the rotation around the Sun. And so we measure the right ascension from the point in the orbit where we have the March equinox. And you measure it east to west, so clockwise. So that's counterclockwise. And importantly, we measure this value rather than in degrees, we measure it in typically in sidereal hours, minutes, and seconds. So yeah, that's an important point to always remember, is that declination is measured in degrees, whereas right ascension is measured in hours, minutes, and seconds, and that can be kind of an annoying convention to deal with, as I'll show you in a few seconds. But you just have to bear that in mind. But the benefit of using these coordinates is that objects always have the same coordinates unless they have some proper motion, meaning unless they have some inherent motion to them, they're actually moving with respect to the Earth. Yeah, so these are typically the coordinates that we use to report the coordinates of individual objects in the sky. So to give you an example, the Crab pulsar, a very famous pulsar, has radic coordinates, right ascension and declination coordinates, 05, 34, 31, 95. That's the right ascension. So we always report the right ascension first and then declination. Declination 22, 00, 52.2. So let's look at the declination first. It's 22, 00, 52. So it's 22 degrees, 0 minutes, 52 seconds. And the minutes here are defined as degrees divided by 60, and the seconds are the degrees divided by 60 divided by 60 again. So to calculate this as a decimal value, you take the 22 plus 0 from the minutes plus 52 seconds divided by 60 divided by 60 is 0.0144. Add those together, you get 22.0144 degrees. So that's fairly simple. The problem comes with right ascension because I've said these are not measured in degrees, they're measured in hours, minutes, and seconds. So we have 5 hours, 34 minutes, and 31.95 seconds. But now the minutes here are defined as the hours divided by 60. And the seconds are hours divided by 60 divided by 60. In other words, a minute of the right ascension is not the same as a minute of the declination. So you have to bear that in mind. So to get a decimal degree value for the right ascension, we take the 5 hours multiplied by 360 degrees by 24 hours. That's one rotation, which gives us 75 degrees. Then plus the 34 minutes, which is 0.566 hours. Multiply that again by 360 over 24 gives us 8.49 degrees. And then the second, same thing, divided by 60 divided by 60 gives us a value in hours. Convert that to degrees, it's 0.133 degrees. So this value in hours, minutes, and seconds is 83.623 degrees. So it's very useful to be able to do this by hand. But if you don't want to, I have linked a calculator, an online calculator to help you do that automatically. Let me just quickly show you how that works. So it leads you to this web page, and you just enter the coordinates in there, press search, and it shows you the coordinates as if they are in hours and degrees, and then they convert them to degrees, decimal values down here, and you can just copy and paste them. And it also gives you the value in galactic coordinates, which I will talk about soon. Right. So just to emphasize one point that you have to be very careful with when you're dealing with equatorial coordinates is that 1 second is not the same as 1 arc second. It's very confusing, but you have to always be mindful whether you're working in degrees or in hours. So a second is a subdivision of a sidereal hour. It's an hour divided by 3,600. An arc second is a subdivision of a degree. It's 1 degree divided by 3,600. So since there are 24 hours in a rotation, which is equal to 360 degrees, and 360 divided by 24 is 15, 1 hour is the same as 15 degrees, or 1 minute is 15 arc minutes, 1 second is 15 arc seconds. So this can be very confusing, especially because they are reported using the same notation, minutes and seconds. But you just have to be mindful of this, unfortunately. It's just one of those things with astronomy. The conventions are what they are. So another thing you have to know about equatorial coordinates is that instead of the right ascension, sometimes we prefer to use the hour angle. So remember, the right ascension is measured with respect to the March equinox, a point on the orbit of the Earth around the Sun. Right ascension, instead, we measure with respect to the meridian. So if you look at the diagram on the right, the meridian is this big circle that we can draw which includes the north celestial pole. So that's the north pole of our rotation axis, and also the south celestial pole. And then it goes through the zenith, which is directly overhead an observer. So if we define the longitude using this hour angle, that's a local measurement of the longitude of a source. So we measure it east to west from the meridian, so that's uh, clockwise. And basically, you can think about the hour angle, also measured in hours, minutes, and seconds, as the amount of time since the source has crossed the meridian, which is the same as the maximum elevation of the source. So if you remember back to those plots that I showed of the elevation of a source as a function of time, they all go up and then they go down in a curve. And that peak, where they are at the maximum elevation, are exactly where they cross this meridian. And so you can think about the hour angle as how long since the source has been at its maximum altitude. And so the hour angle at 0 is where the source is highest in the sky. And then it increases as the day proceeds and the source gets lower in the sky. So you can convert between the local hour angle and the right ascension using this equation. The hour angle is the local sidereal time minus the right ascension of the object. So this is why we tend to measure right ascension in hours, minutes, and seconds rather than degrees, is because it makes this conversion to the local hour angle easier, or historically that's been how people have preferred to do it. So this hour angle is useful because it's a local measurement of the longitude, whereas the right ascension is defined with respect to an equinox, which is difficult to locate on local coordinates. So if you want to convert, as I'll show you later, if we want to convert between equatorial coordinates and horizontal coordinates, you can't use the right ascension. You have to use the hour angle, because the hour angle is the local measurement of the longitude that you're actually able to see on the sky from the observer's point of view. Yeah. Another important thing that you have to know with respect to these coordinates is that we have to define something called the epoch. So we know that these equatorial coordinates are defined with respect to the celestial plane. That's the plane of the Earth's rotation. But the Earth's spin axis actually precesses. It's changing very slowly to the degree of one rotation every 26,000 years. So these coordinates are actually changing very, very slowly. So if you specify a right ascension and declination of a source, those coordinates are going to change very slowly as the tilt of the Earth's spin axis changes. So if we want to be consistent with our coordinates, you have to specify an epoch, which is a time that freezes the coordinates in place. So to give you an example, since 1984, astronomers have used J2000 coordinates, which means that we use the RA and DEC values as if they were measured at 12 UTC on the Julian date 1 January 2000. So when we measure right ascension and declination, we have to do a small conversion, a correction, to change them so that they would have been as we observed them on that date in January 2000. And that way those coordinates always stay the same. Before we used the J2000 coordinates, we used B1950 coordinates, which were measured from 1 January 1950 in Besselian years. So I won't go into Besselian years. They're basically a defunct or out-of-date way of tracking years devised by Friedrich Bessel, who you may know about. But we don't use that system nowadays for a variety of reasons. But some objects that were discovered long ago still have B1915 coordinates. So, for example, the Crab pulsar, if you look at in the pulsar catalog for this pulsar, it actually has two names. You can call it BO531 plus 21, or you can call it JO534 plus 2200. And those correspond to the coordinates measured using the different epochs. So the old name is measured using is using the coordinates measured from the B1950 coordinates, and the newer one is from using JO534 coordinates. So sometimes it's a bit annoying trying to keep track of which coordinate, which epoch is actually being used. So we switched to J2000 coordinates in 1984. We'll probably switch to J2050 coordinates within our own lifetimes. So that's a decision that will be up to the International Astronomical Union. I'm not aware of any talks or about changing those coordinates, but they will have to change at some point, at which time all of our coordinates will change again. So it's going to be a big pain to convert to these new coordinates, but it's just something that you have to do because the Earth's axis precesses. Right, so the third coordinate system is called ecliptic coordinates. So they are very much like equatorial coordinates, and they are centered on the Earth. But instead of using the celestial equator as the fundamental plane, as you can see on the diagram on the right, the celestial equator is perpendicular to the rotation axis. Instead of that, we use the ecliptic. And the ecliptic is the plane defined by the rotation of the Earth around the Sun. So we use this plane of the rotation to measure positions of objects. So most planets and small local bodies within the solar system, their orbits are only very slightly inclined with respect to the ecliptic. So it's often useful to define the positions within the solar system using these ecliptic coordinates. But so this is the system that was used most commonly in ancient astronomy and astrology systems. For instance, that's the system that was used to define the zodiac signs. But in modern astronomy, as far as I'm aware, they're sometimes used for local, like solar, if you're tracking objects within the solar system, if you're doing observations of Mars or Jupiter or something. But for the most part, it's not used very often. And then finally, I want to talk about galactic coordinates. So that's the fourth coordinate system. And in this one, we use the plane of the Milky Way galaxy as the fundamental plane. So because the Milky Way is a spiral galaxy, it's very nearly flat. And you can use an approximation of that plane of the Milky Way to measure coordinates relative to that plane. So we define the latitude, the galactic latitude B, as 0 degrees within the plane of the galactic equator. That's 0 degrees, and then going up above the plane is plus 90 degrees, and below the plane down to the galactic South Pole is negative 90 degrees. And to define the longitude L, We look at the galactic center, that's the 0 degrees, and then we measure counterclockwise from 0 around n degrees. So these coordinates are most useful for understanding how objects are actually distributed in the universe. So we can use uh, equatorial coordinates to track objects as if they are observed from the Earth. But if we actually want to understand how these objects are distributed in space, without the effect of looking from the Earth, it's almost like we're standing outside and looking as an outside observer outside of the galaxy. So, for example, if you've seen this, I'm sure you've recognized this plot on the left, or this image of the Meerkat galactic plane. These are in galactic coordinates, so that the galactic plane is all in a line uh, in the center of the image, and that allows you to get some sense of how objects are actually distributed within the galactic plane and the galactic center. It's also useful to distinguish if you're studying extragalactic sources or galactic sources. So if you are looking at sources from distant galaxies, those galaxies will be distributed approximately isotropic, right? So they from all around us. And so if you plot them on a galactic latitude and longitude map, like the one on the right, they should cover the whole map more or less isotropically. Whereas if you are looking at galactic sources, things which are in the Milky Way, for the most part, they will be confined to the plane, a few degrees around the plane, except if they are very nearby. If they're very nearby, they might be sort of underneath us or off to one side. But for more distant objects, they should be confined to the plane. So so this is useful to know if you don't have some distance measurement, you can still tell if they are coming from out other galaxies or within the galaxy. And you can also do things like uh, uh, studying the proper motion of sources. You can get an estimate for their age. So if we assume that most sources are within the galaxy, are born within the galactic plane, older sources should be further away from the plane, so they should have had more time to move to higher latitudes, whereas younger sources should be more strictly confined to the plane. So you can do some interesting stuff with that as well. These are just some examples that I know about from the world of pulsars and transients. Right. So uh, here are the equations that you can use for converting between these different coordinate systems. I'll send around these slides. If you want to, you can use these equations later, or otherwise, if you just search for this or in any astronomy textbook, you will find these equations as well. But I just want to walk through some important facts about them. So when we are converting between equatorial and horizontal coordinates, as you can see, we have to use, instead of the right ascension, alpha, we have to use the hour angle. And then we can use the hour angle to get back to the right ascension. But in the conversion, we have to use the hour angle because the horizontal coordinates are local coordinates. You have to use the local measurement for the longitude, which is the hour angle. And you also need to know the latitude of the observer, phi, in order to calculate or to do this conversion between equatorial and horizontal coordinates. When you're moving between ecliptic and equatorial coordinates, um, here you both are centered on the Earth rather than the observer. So you don't have to use our angle. Here you can use the right ascension alpha, and you don't have to know the latitude of the observer, but you need to know the obliquity of the ecliptic. So that's basically how the ecliptic is inclined at a given moment. And there are equations that you can use to calculate that, or you can just look it up. But yeah, then you can just use those equations directly. And then when you're moving between galactic and equatorial coordinates, you can again use right ascension and declination, but you need to know a few constants. So you need to know the right ascension and declination of the north galactic pole in right ascension and declination. So that's where these 27.4 and 192.25 constant values come from. Yeah. So you can use it's useful to have these equations within your arsenal. Sometimes I've had to use them by hand just to try to understand exactly what I'm doing. But in general, nowadays, you don't have to do these by hand. You can use AstroPy to do them automatically. That's a Python package that does a lot of these conversions. It has them built in. It has all of the unit conversions. You can just tell it, give it some coordinates and specify the unit and the coordinate system and ask it to convert it to different coordinates and units. And it does all of that automatically, and it's very easy. Um, so you don't have to know these off by heart, but I think just to know what each of these coordinate systems mean and how they relate to one another and when they are useful. That's what I want you to get away from this lecture. So before we end, let me just go to questions. Let me quickly just summarize everything. So astronomers usually measure time in modified Julian days, NJDs, which is a decimal count of days since some time long in the past. Sidereal time is an important concept, and it's based on the motion of stars relative to the Earth. It allows us to track when astronomical objects are visible in the sky. And then there are four commonly used coordinate systems: horizontal coordinates, which measure the elevation and azimuth with respect to an observer; equatorial coordinates, RA and DEC, which measure positions with respect to the Earth's plane of rotation; ecliptic coordinates, lambda and beta, which measure the positions with respect to the plane of the Earth's orbit around the Sun; and then galactic coordinates, L and B, which measure the positions with respect to the plane of the Milky Way. And if you know those four coordinate systems and know what they're doing, you're solid. So that's it for now. Let's go to some questions. So I can see that there is one for in the chat. Annalise is saying the reason for JD starting at noon is so there's no change over the day value during the observation time at night. Yeah, that's a good point. Thanks. Any questions you can type in the chat or ask directly.
Yeah. Hello, Tim.
How's it?
Joseph.
It's Joseph. Yes, you can go ahead.
Yeah. If we are writing a proposal for observation,
Yeah.
we specify the location of the object as well as the time it can be observed, or you just specify the location and the station will know when to observe it?
Yeah, so it depends. In my experience, it depends on the observatory. For Meerkat, for example, you only have to specify the right ascension and declination, and then they calculate um, uh, uh, an appropriate schedule for you to make sure that all of your sources are going to be up in the sky. So they have a dedicated team who do the scheduling to try to get everything up in the sky. But you have to, um, but for some observatories, I think for parks this is the case. You have to demonstrate exactly when in the day your objects are going to be up in the sky. So you use a tool like the one that I showed, which says which LSTs they're going to be observable, and then specify how long you want to observe them. So yeah, in general, you're going to report your coordinates using equatorial coordinates, RA and DEC, and then sometimes, depending on how the scheduling works for the telescope, you have to specify some LST ranges as well. Paul,
Oh,
your hand is up. Oh, okay. Last chance for questions.
Oh, sorry, Ken, if I can ask.
Yes.
Just it's the conversion from B 1950 to J 2000. Any tools that you're aware of or easy ways of doing that? And I've tried to look at it a few times and actually ended up with two different tools and they gave different answers. So it doesn't feel like an easy process.
Yeah, I know you can do it in AstroPi. There's a good function to do that. But like I haven't found an online tool that does that easily. I haven't found too many instances where I've had to do that. So usually I just bash it into AstroPi and get that. But yeah,
Okay, thanks.
cool. And then Annalise says, I think there are limitations of the equipment too. For example, how low a telescope can be used, even though the object may be up. Dome dependency. Yes, very true. So for Meerkat, um, I think the elevation limit, you're not going to be able to observe something much beyond 30 degrees, positive 30 degrees declination. But that's just because it's not going to be up on the horizon, above the horizon. Some telescopes, as you say, it can't go down or above, it can't go down below a certain elevation above, on the sky, so that's another limitation there as well. But I'm not familiar exactly with the values for individual telescopes. They're all in the um, documentations for those telescopes. That each one has its own quirks and specifications that you have to be mindful of. Annalyn, you have your hand up.
Sorry, can you hear me?
Yep.
Okay, I just want to know when we're calculating coordinates, to what decimal point is acceptable in astronomy?
Yeah, well, that
for
depends.
degrees.
Yeah, I mean, it depends on how precisely you know the coordinates, right? So if you, so with Meerkat, you can localize an object to a few arc seconds, so the resolution is a few arc seconds, and so you can only report the coordinates down to errors within that range. So you always have to report the errors as well. For other objects, uh, they're very often very poorly constrained in, like, if you're doing gamma ray or X-ray astronomy, sources could be constrained to a few degrees on the sky. So yeah, it just depends on your angular resolution.
Thanks.
Sure. Okay. Any other questions before we end? Not seeing anything. Let me just quickly go to the schedule. So in 2 weeks' time, we're going to be doing some radio telescope basics, talking about the primary antenna elements. So we're getting back into the kind of nitty-gritty of how a radio telescope actually works, how it does its measurements, and the different components that make up a radio telescope. So, and then after that, we have 2 lectures on radio interferometry, and then time domain astronomy, 2 lectures, and then one final one on radio stars. So yeah, we're about halfway through the schedule. Yeah, see you all in 2 weeks, and I hope you enjoy your weekend.
Great. Thanks very much.